Oh, good, you're back. I was worried. All right, cool. So, continuing on then, we got our exponential functions we left off with. There's no issues here with plugging in whatever we want for x, so our domain is going to be negative infinity to infinity. Some other functions that you might have seen, and we might see as we go along, logarithmic functions. So if you have an exponential function, the way to undo that is the logarithmic function. So these are the form log b sub x, where b is a number called the base. And essentially what this is checking is if I raise this number to some power, how do I get x? What's the power that I need? And so here we have to make sure that what's inside the log is positive. So there's nothing we can raise to any power to get 0, so we can't include 0. We can't raise some base number to a power to get a negative number, so we can't plug in negative numbers. And so we go from 0 to infinity. So that's our domain for those. Some other functions here, and they're on the tables. I don't want to read the tables to you guys. Sine, cosine, tangent, cosecant, secant, and cotangent. Remember that the second row is just 1 over whatever's above it. So cosecant is 1 over sine of x. So the reciprocal. Secant is 1 over cosine of x. And cotangent is 1 over tangent of x. So this talks about what those domains are for those functions. And then don't forget that tangent is just sine over cosine, which means that this is really just cosine over sine. And then things you probably haven't dealt with before, and I don't know if we're going to get to this semester, but I'm going to put up here as functions you might remember anyway, are the inverse trigonometric functions. So inverses, what they do is they undo whatever it is that was done before. So if you took the sine of x, you would get some value. If you plugged that value into sine inverse of x, or arc sine of x, you would go ahead and get whatever the x was that you would input. The x you would input for the sine of x. So these are those functions. Not going to spend a lot of time on them. And then when we're going to graph functions, we have a few different things we can do to our functions to move them around, shift them, that sort of thing. So for vertical and horizontal shifts, suppose we've got a positive c. That way we can talk about these the same way. To obtain the graph of f of x plus c, what we're doing is we're taking our function values and just moving them all up. So in other words, if I had my value was 10 and c is 2, then I shift my 10 up 2 to get to 12. If I'm taking and subtracting c from f of x, then we're shifting downward. So again, if we had a value of 10 and we subtracted 2, it'll move 2 downward. Now, the less intuitive thing is what's happening when you put x minus, or you subtract or add the c within the parentheses. So if we have of, in parentheses, x minus c, we're shifting the graph c units to the right. So just to see this really quick, if we have f of x equals 2x, and then we had f of x equals 2, well, let c be 1, x times x minus 1, we'll call this g of x. When we graph f of x, what we're doing is we're just doubling whatever the values are. So 1, 1, 2, 2, 3, 4. But now for g of x, when we go ahead and subtract 1 from whatever the value is, it'll change where things are. So if we had 0 before, 0 is now actually going to be 0 minus 1, or negative 1, and then negative 1 times 2 will be negative 2. And then if we plug in 1 for x, because we're subtracting 1, we go ahead and get 1 minus 1, which is 0, and then that gives us 2. And then we continue this trend with g of x. But notice how subtracting within a value directly from the x goes ahead and moves things to the right. And so similarly, if we add something to the x before plugging in anything, we're going to shift the graph over to the left. So just shifting vertically and horizontally, that can happen with graphs if we want to transform them in some way. We also can go ahead and stretch our graphs and reflect them. So assume for a second that c is greater than 1. So it's positive, and it's not some sort of decimal or fraction that is less than 1. If we multiply our function by a constant value, we're essentially going to take all the values from the function and multiply them by that much. So this will stretch the graph vertically, so it'll make it longer. If we go ahead and multiply by 1 over c, essentially we're now dividing by something, and so that's going to take our graph and shrink it down vertically by a factor of c. Then there are these next two where we go ahead and shrink and stretch the graph horizontally. So if we're multiplying by c, then what's happening is when we put in a specific value of x, we are going ahead, and so here if I said we had f of x equals x plus 1 and g of x equals 2x plus 1. So with x plus 1, what we're getting is this point, then this point, then this point. We end up with just a line here. But if we go ahead and double x first, it doesn't matter so much for 0. But then for the next one, we'll be doing this. And then, should have given myself more room here. We'll have this point, and essentially it'll be the same idea, but we've now taken this graph that looked like this, and we are now squeezing it down so it takes less space horizontally, because our values for x are more impactful and they cause things to grow bigger. But if we are dividing by the x by some value, then essentially we're going to have the opposite happen. So if we had h of x equals x over 2 plus 1, then here again we'll have the same point, but then we'll have to get to 2 before we get to this 1. And now we will be dealing with a graph that looks like this. So again, now it's taking that same idea and stretching it out some. If we want to go ahead and flip things over the x-axis, we'll just take all of our function values and multiply them by a -1. So, in other words, say this is f of x, then draw this a little more carefully. This will be negative f of x. Essentially, we just took the outputs and made them negative, or the opposite sign of whatever they were. And then if we have f of negative x, we're reflecting about the y-axis. So if we had something like this was f of x, then essentially what we're saying is all of our inputs become negative. So this will be f of negative x. We also can do algebra with functions. So we can go ahead and add two functions together. So if we say f plus g in parentheses of x, we're really saying f of x plus g of x. If we say f minus g in parentheses of x, we're saying f of x minus g of x. If we say f times g in parentheses of x, that's f of x times g of x. And if we have f over g of x, then that's f of x over g of x. Now here, importantly, we cannot divide by 0, so that is something that we'll have to keep in mind with the domain. In all other cases, though, we have the combined domains of f and g. So in other words, we need to be able to put something into both of them to be able to get an output. The last thing we have here, and what we'll see a lot of on the homework, are composite functions. So if we have two functions f and g, the composite function f compose g is going to be f of g of x. So this can manifest itself in a number of ways. Let's say, for example, we had f of x equals 2x plus 1 and g of x equaled x squared minus 1. In that case, f of g of x, essentially what we're doing is wherever there's an x in f, we're replacing it with the entirety of g of x. So normally f of x is 2x plus 1. However, the x is getting replaced with x squared minus 1. So that means we have 2x squared minus 2 plus 1, or in the end, 2x squared minus 1. So this is f of g of x. Meanwhile, if we had g of f of x, now what we'd be doing is we'd be taking the x portion, I really need more colors, we'd be taking the x portion in g of x and replacing it with the entirety of f of x. So we would have 2x plus 1 squared minus 1. So we'd be doing just g of x, and then where x was, it gets replaced with all of what f of x is. So we'll need to multiply this together. So 2x plus 1 times 2x plus 1 minus 1. So if we do FOIL first, will be 4x squared. Outer will be plus 2x. Inner will be plus 2x. And then last will be plus 1, and then minus 1. And then combining our like terms, we get 4x squared plus 4x, and this will be g of f of x. There are a lot more examples in the EchoPen lectures of composite functions and domains and ranges. And so if you find yourself struggling on the homework, I would definitely recommend checking those out. I'm trying this semester to treat this function part as a review. So for some people, I'm hoping that this shorter video on functions is enough. But if it's not, we've got plenty of other material for you, and we've got the discussion boards as well. So definitely feel free to post and ask questions. The next video will be about tangent lines and secant lines. And will hopefully be the first newer material for most people.